Thank you very much. Thanks Enrico, Daniele for the invitation. I think I was here at the first edition. Probably I was one of the first speakers 4 years ago, 2018. I'm very happy to be back here. My main activity is not exactly on high energy physics, so I'm not a high energy physicist in fact. But in the last few years, we've been working a lot on quantum machine learning. And what I'm going to present today is a very small project, a sort of independent project, born almost by chance from a collaboration with Pietro Govoni and his group at the University of Milano Bicocca. And it is about comparing quantum and classical machine learning approaches for analyzing high energy physics data. And the main message here is not about advantage at all. So I'm not really focusing on which is best in terms of giving an effective advantage, but it's just the interest of comparing the two approaches, the two algorithmic approaches in comparable conditions, under comparable conditions. So first of all, let me give credit to the people with whom I've been collaborating. And it's funny that this project was born in 2020, just within the full pandemic period. So it is nice, actually not very nice, but it is funny that I never met in person these people. But we shared a lot of discussions online with Pietro, and above all these students, Davide first, and then Aurora, were bachelor students, in fact. So the project I'm going to present are bachelor students project. Davide was a PhD student at the time, and now he's at CERN. So I'm not a high energy physicist, but the main motivation comes from the huge amount of data produced at the Large Hadron Collider that most of you might know. This is the largest particle accelerator in the world, based in Geneva. It's about almost 9 kilometers diameter ring, 100 meters below the city of Geneva, which after a few acceleration stages allows to make protons collide with other protons at incredible energies. This is where the famous Higgs boson has been discovered about 10 years ago. This is Peter Higgs himself, next to one of the big detectors that I'm going to talk about. So there is huge motivations from a computational point of view coming from the LHC, because, as you may imagine, this particle accelerator produces a huge amount of events, and so data that can be analyzed by employing sophisticated computing tools. So one of the big challenges in terms of computational tools involving, again, a combination of high performance computing and strong infrastructure is the fact that this huge amount of data are produced at an incredible rate, on the order of petabytes per hour. And so already managing this huge amount of data requires the involvement of several nodes in the world. And this motivated the build-up of the World LHC computational grid, which is this incredible project involving 170 sites, 42 countries, and really being able to process an incredible amount of data. This is extremely interesting. However, there is more recently another interest in terms of computational challenges, which is increasingly involving machine learning. And this motivation comes from the fact that among this huge amount of data, there are some processes in which the signal is just a tiny amount over a huge background of unwanted processes. And machine learning is extremely effective in trying to discriminate between signal and background, trying to extract information about the signal that you are seeking for over a huge background, which gives exactly the same products of scattering. Let me show you this by a Feynman diagram. The physicists in the audience might be familiar with this, but also for the non-physicists, this is an easy way of picturing what's happening when two protons collide with each other in the detectors. There are the two protons represented by these three lines, one on top and one at the bottom. As we know, the standard model of particle physics teaches us that each proton is made up of three quarks. So the three lines correspond to the three quarks of each proton. Now, one of the two quarks of each proton, when the two protons collide, emit particles. And one specific process occurs when the two particles emitted by the two quarks are two vector bosons, elementary particles in high energy physics. And these two bosons, these two vector bosons collide, they make a scattering process. And at the end of the story, you will have the two protons being completely dismantled. They are completely, they fall apart. And you have a given series of products of this scattering process. And these products are other elementary particles, neutrinos, muons, other quarks, and so on and so forth. Now, interestingly, this is the specific process we are interested in this scenario. However, there are several other processes that contribute with exactly the same products in the detectors. And it is, from the detector point of view, it is impossible to discriminate if the process that has occurred is a vector boson scattering, so one of these top graphs above, or simply the emission of a single boson that has undergone multiple emissions of other particles, and that the detector will just see the very same products. So these processes above, without going into the details, are what we will define the signal. And these processes at the bottom is what is defined as the background. Now, normally in this collaboration, this is again a small collaboration. We do not work on real data coming from LHC, but this collaborator at Milano Bicocca allowed us to employ computational tools that generate these signal and background events by Monte Carlo, by codes that belong to the collaboration, and specifically to the CMS collaboration. One of the big detectors, the other is Atlas, at which the Higgs boson was discovered. So just to give you an idea, the vector boson scattering signal has a weight that is about 1/10,000 probability to occur over the background events. So these are the main background events, the ones that we want to discard. And this is the tiny vector boson scattering signal that these people want to detect. And to do this, they can simulate about more than 50 variables corresponding to the particles emitted in this process. And when I will talk about variables in this talk, I mean the momenta, the masses of the particle products. In a machine learning scenario, of course, it is important to properly select the variables. And this is done on a pre-selection procedure in which it is generated the probability distribution for each of the variables. And we check if the probability distribution of the signal and the background is similar or not too similar. So for the machine learning purposes, this variable would be a good choice because signal and background have different statistical distributions, and they help in discriminating the two. The machine learning scenario is the general one, so I'm not going to introduce it further because Enrico has done it already. And as you might know, you can move between supervised, unsupervised, and reinforcement learning. Here we will use supervised learning on neural network algorithms or the quantum counterpart of neural network algorithms. And basically what we need in terms of machine learning capability is a classifier. It's an algorithm that is able to discriminate between an event that can be classified as signal and an event that can be classified as background, which has to be discarded by our set. And the way to do it is supervised in terms of learning. It's very similar to training a neural network, a deep neural network, to discriminate between cats and dogs for example, pictures when the cats and dogs pictures are labeled. So you train the net on labeled data in such a way that when you insert as an input the unlabeled data, the network is able to classify it correctly, as in this case. More generally and formally, machine learning deals with having some input data, building some function of this input data and parameters, which are the weights. And through a minimization procedures, you have to train this function to recognize the input and give the correct output. What we have done is basically to test these two machine learning approaches using a classical deep learning procedure. So there is a deep learning, a deep neural network with an output, just an output node, which has to give the response, yes, this is signal, yes, this is background. And this is done by minimizing the cost function. In this case, the cost function is the usual cross entropy for people that are interested in machine learning. And then the test is performed on unlabeled data to see if the training was correctly performed. Now, on the quantum counterpart, quantum machine learning means a lot of things, as you might imagine. Enrico has shown you a few of the possible definitions that we can give to machine learning, to quantum machine learning. In this case, I really mean the quantum counterpart of neural networks, which you might call quantum neural networks, or in general, quantum computing models for artificial neural networks. And there can be different, which belong more or less to categories that can be broadly speaking, said to be different from each other. Enrico has mentioned one specific algorithm we have introduced in Pavia a few years ago, which is a quantum version of the perceptron that they have nicely generalized. And Leonardo has talked about something which is which falls in the category of quantum neural networks, as I will mean in this talk, which is basically a parameterized quantum circuit. A quantum circuit made on a digital model of quantum computer in which you can parameterize your weights in a unitary operation that is a function of these weights, and build some output function after the measurements over which you define a loss function and minimize classically this loss function. So this is intrinsically an hybrid quantum classical approach, which might bring or not bring necessarily quantum advantage, but it is still interesting to investigate how these quantum versions of the neural net or of the variational circuit behave as compared to a classical neural network. So Marcello Benedetti has shown a few years ago that all these models fall into the general class of hybridized quantum systems, parameterized quantum circuits, in which you basically input data, you build your parameter. Sorry, I'm really going out of time here. So we use our version of these parameterized quantum circuits, in which we use a unitary operation to map the data, the classical data, and then a variational unitary operation where the weights are encoded. And after the measurements, we build the output function and the cost function. Let me skip the details. This is run on IBM quantum computer. Of course, as academics, we are not favoring any of the companies. All of them that we've been hearing today are really interesting and promising, but credit should be given to IBM to start, as Fabio Scarifimuto has told us this afternoon, to start a huge educational campaign. And now this is really spread, and students can run their projects and maybe obtain original results, even on chips, on simple 5-qubit chips as the ones that have been used for these projects. Now, very quickly to the result, what we have found is that the figure of merit that is typically used in this case, so the relation between what is called the true TPR, the true positive rate, and the false positive rate, meaning the probability of that a positive event is correctly classified on the unlabeled data after you have trained your quantum neural network, and the false positive rate, which is the probability that a negative event is classified as positive, something that you don't want. And ideally, this graph should have a behavior that goes to an area below this curve that is 1. So the behavior of this straight line is the flipping coin behavior, 50%, completely random. If this curve goes up to an area which is about 1, it means that you are correctly classifying 100% or towards 100% of your unlabeled data, which is the good figure of merit for this classification. Those were the two best curves obtained with the classical, the green one, deep neural network, and with the quantum neural network approach. And you see that they are comparable. But this is not so interesting per se. What is interesting is to see how they behave as a function, for example, of the number of variables used during the training procedure. And if we see that the classical, the deep neural network approach, of course, increases its performances, which is the area under this receiving operating characteristic curve, when the number of variables increases. However, the quantum machine learning, the quantum neural network is much more spread in terms of results if you perform the training multiple times. But the best results are already quite good, even for a very small number of variables used in the training, which is sort of, I mean, these are few points, but it is sort of interesting and keep in mind. Another test that we performed is to compare the two by using the same number of qubits or the same number of variables in each case, and performing a scan on the number of events used in the training set. And as you see, typically the classical machine learning needs many more events in the training set to perform well, while the quantum machine learning requires less than 1,000 events in the training set to perform comparably well and with a distribution that is almost flat. Nicely, again, this is a small project run by bachelor students. In parallel, we found that collaborations involving many more people and heavier, let's say, resources on heavier hardware chips found very comparable results. And the conclusions are, if you want the take-home message, the main take-home message is that the quantum neural networks seem to perform comparably well with the deep neural networks, but they start to converge to the same behavior, to the same figure of merit for a much smaller number of training events and for a much smaller number of training variables, which is per se interesting to understand. We do not know why. It is interesting per se to understand why this happens at the theoretical level.